And this is the first thing. Insects only feed upon food that is considered unfit, nutritionally poor, dead, or dying. If you have never heard this before, I'm not surprised. I never heard it at Cornell. I never heard it at UF. This is something that I had to realize, and I came to the conclusion after I had left school, which sometimes I say that was the beginning of my education. Once I realized that the insects were not competing with us and that they were only eating crappy food, I understood, aha, the role of insects is not what I was taught before. They actually have a very important role, and that is to clean things out. Sometimes they're referred to as garbage collectors. It's a term that's not that far off, to be honest with you. So, if I have a couple grasshoppers here, and I were to ask you, what are they going to do? If you give them two food sources, and they have two choices, they got a choice between unhealthy food and healthy food. Most of you, especially if you hadn't seen what is listed above, would say that the grasshoppers would distribute themselves on the healthy food, some would be on the unhealthy food. Why? Because grasshoppers eat everything. Therefore, they really don't care what they're eating. And that's what I would expect most of you to say. But that's not what they do. Right. If you give them a choice, they don't equally go on both sides. Instead, they always choose the unhealthy food. This was a shocker. If you're hearing this for the first time, it is also going to be a shocker for you. So there's a lot of feeding into you that I'm going to need to do in order to convince you of this truth. So where am I going to begin? If I'm going to convince you that insects are only eating crappy food, what is the first slide that I should come up with? I'm like, oh, I got one. Let's talk about the dung beetles. So the elephant dung beetle goes after, no surprise, elephant dung. It loves the stuff. I mean, they are on it within seconds to minutes after it's dropped. And I have heard of cases from other entomologists that they are attacking the dung before it even falls off the back of the elephant. That's how much they love this stuff. Is any of us competing for that? Are we jealous because they're eating elephant dung and we are not? And so when you hear that insects are competing with us, I would say, no, they're not really. Some of you might say, well, cherry-picking the elephant dung beetle, I don't think that's really appropriate right now, but this is not just about the elephant dung beetle. Did you know that there are 7,000 species of dung beetles? 7,000. This is not cherry-picking. There are 7,000 species going after elephant dung, giraffe dung, human dung, dog dung. It doesn't matter. They've got all of the stuff covered. And so because of this, we know that there's at least 7,000 dung beetles, in addition to many other insects that will attack dung. And so therefore, this is not a food source that you and I are competing with them in. Termites, not competing with us either. They're eating dead wood. Predominantly dead wood. That's the key word here. They're not going after live trees. They're going after dead wood. This is what they specialize in. They are also not competing with us. We are not getting 2x4s for lunch today. We'll be getting some pizza. If we were given 2x4s, you look at it thinking, what am I supposed to do? Eat this? Because you know you can't eat it. Termites can, you cannot. Therefore, again, we are not competing with insects. Love bugs. There's a reason why they're called love bugs. This is still a family show, but every once in a while I'll throw up some of these slides. Love bugs are known for doing the wild thing, and they're found in copula almost all of the time. They specialize in feeding on decaying vegetation. Not just vegetation, but decaying vegetation. And so because of this, they're also not competing with us, because when vegetation starts to die, we don't want to eat it. It looks gross. It gets kind of blackish or brownish, gets a little slimy. They love this stuff, and they're really good at eating it. And their numbers get to be so large that during 2 times of the season down in Florida and in Louisiana, they can be attracted to highways as they're attracted to the aldehydes coming from the exhaust of vehicles, and they will plaster themselves on the windshield in a way that you've probably never seen before. I was told, whatever you do, Tom, do not turn on the windshield wipers. One time, it got really, really bad, and I turned on the windshield wipers, and I will never make that mistake again. I had to pull over and do my best in order to clean them off. So this is showing you how good they are at eating decaying vegetation. Clothes moths, also not competing with us. We're not eating our clothes. We're not having it for lunch. We're not having it for dinner, and I'm sure we didn't have it for breakfast. We don't eat our clothes, but there are a minimum of 3 species of clothes moths that do eat clothes and specialize in various wools and linens. They don't go after polyester, but they do go after some other things. This is also a case of they're not competing with us. Dermestid beetles eat decaying meat and hair off of bones as well. The dead insects in my insect collection. These insects are not competing with us either. They're very good at what they do, and they're used in museums in order to clean off skulls when they're put on display in a particular museum. They do a better job of cleaning off the meat and the hairs. They also don't discolor it in the same way that some chemicals do, and because of this, they have a place, an important place. So going after decaying meat is something that some insects do. We're probably more familiar with the blue bottle flies and the green bottle flies, the callitorids, because they will go after deer or any animal that's on the side of the road, and they'll do it very quickly. Within 10 minutes, you will have your first fly on the dead deer on the side of the road. It's been timed. We also know that it's as little as 30 seconds, because that was also timed by a friend I know who did forensics. So they're very good at what they do. And they're also not competing with us. Some of you may differ, because if you see a dead deer on the side of the road, there's always someone in the crowd who will pull over, quickly throw the thing in the back, and then take it home and see if it's usable meat, because it's venison and it's free. But generally speaking, once it gets decayed to a certain point, none of us will really want to eat it. Cockroaches, need I say more? They're certainly not eating the same stuff that you and I are eating. I mean, they're being collected behind what? The refrigerator, you can find them in the pantry, eating lots of crumbs, stuff that you and I don't want to eat. Fruit flies. I won't bring back any bad memories of genetics class, but the fruit fly, Drosophila melanogaster, usually found around overripe fruits, overripe vegetables and other organic foods that are damaged, fermenting, or in an otherwise state of decay. If I'm going into the store and I see some fruit flies flying around the tomatoes, do I grab the tomatoes? I actually do. Because I know that they're probably only going after one bad tomato or two, and if I go digging far enough, I can find several dozen attacking the one bad tomato that happens to be in the store. Once again, they're not going after the good stuff that I want to eat and my family wants to eat. They're going after the decaying stuff. These guys too, stored product insects, specialize in what they do. They don't go after crops in the field. They only take it after you remove them and put them in a storage grain bin, silo, warehouse. Then the stored products come out. Indian meal moth, #1 stored product pest in the world. Tribolium, red flower beetle, also very popular sawtooth grain beetle. These are all insects that specialize in, shall we say, dead food. Because once it is harvested, it is taken and put it in, and at that point, it's not living anymore, and it's dying, and we have insects that specialize in taking care of that kind of food. So this does beg the question, because, you know, many, if not all of you, are farmers, and you're saying, thanks so much for the elephant dung slide, I really appreciate that, but this isn't really relevant to me, because I'm a farmer, I raise crops, I've got plants, and I've got insects attacking in them and they need to die. This is what I need to do, this is my job, talk to me a little bit more about this. Because that's very different from what you've been saying for the first few slides. No, it's not. It is not any different than what I've just been talking about. Those insects that are attacking plants are only going after bad, decaying dead, dying plants. That's it. They don't go after healthy plants. Take a look at this. This is a picture I took in Hawaii. What do you see? You see a lot of green. You see trees with leaves, bushes, grass. Why haven't the insects consumed this? You ever thought about this? Why? There's plenty of food there. Oh, well, it's on an island. They just haven't found it. Well, that's bullcrap. Because I was there. I saw a lot of plant-feeding insects. But they have not decimated the island. It wouldn't take much. It's only about 20 by 30 miles. It's a relatively small island. And there's a lot of vegetation on it. Why is it not being consumed? This island should have been cleaned out of all of its vegetation hundreds of years ago. You could give them maybe 1-2 years, and insects should be able to clean out an island this size. But they haven't. Why is it that some insects are going after some plants and not others? Why is it that some plants continue to grow while others get consumed? This is part of the reason why I'm here today. It goes to, what is a healthy plant? That's really what I'm getting at, isn't it? Because if you need to know what is a healthy plant, you need to have some way of defining what is a healthy plant. Can anyone tell whether or not this is a healthy plant? With absolute certitude. If I was holding a gun to your head and said, I'm going to pull the trigger if you get the wrong answer, how sure are you that this is a healthy plant? Or, conversely, how sure are you that this is an unhealthy plant? Can you tell? I can't. Some say if it's tall, it's healthy. Bullcrap. Because that means trees are healthier than shorter plants? It doesn't work that way. We can't use that. Some say, does it grow fast? Well, if it grows fast, it must be healthier. There's certain amount of truth in that. But just because it grows fast, that makes it healthier? Are you kidding me? Are you telling me that bamboo is the healthiest plant in the entire world? I can tell you it's not. We've got healthy bamboo and we have unhealthy bamboo, so that's not going to work. What about if it's green, or even better yet, dark green? At that point, we should be able to tell whether a plant's healthy. That's also bullcrap. Because I can take nitrogen and put it on a plant and green it up. And it may not necessarily be healthy. I can also take iron and put it onto a plant and green it up. And that also doesn't necessarily mean that it becomes healthy. In some cases, I actually make it less healthy, despite greening it up. So there's much more to it than that. Will it flower? Some people say if you get flowering going on, the plant is healthy. Certain amount of truth in that, I'm not going to deny it, but that means only the angiosperms, the flowering plants, are healthy. We can't use that. That's not a good marker. That's not scientific. Some would say it has a good root system. A certain amount of truth to that as well. But the root system is not the defining factor in whether or not a plant is healthy. Some say it's extensive. It may not be as extensive in other plants. Corn has a short root structure. Other trees, for example, have a more extensive root structure. Some of them have tap roots that go down 50 to 100 feet or more. Does that mean it's healthy? No. You cannot go by the root system. Plus, would you want to? Who's going to be digging up plants in order to determine whether or not the plant is healthy or not? Nobody is going to do that. Does it grow even? I hear this a lot from the farmers. Why? Because they want to be able to harvest at the same time. That doesn't make it healthy in and of itself. That just means that it's growing even. So this is also not a good indicator of plant health. And some people, homeowners especially, will say, oh, it's healthy because I grow it myself in my garden and on my porch. Therefore, trust me, it's healthy. Am I supposed to trust that someone is telling me that they got healthy plants? No, I can't do that either, because I know a lot of porch plants are not as healthy as they could be, and sometimes they are still attacked by insects. So, how do I determine what is a healthy plant? This is how I determine whether it's healthy or not. photosynthesis. It's all about photosynthesis. Every plant photosynthesizes. Big plants, small plants, wide plants, any type of plant, green, chlorophyll, they're photosynthesizing. The goal is to take carbon dioxide absorbed through the stomata and water, usually through the roots, also through the stomata, in order to make sugar, C6H12O6. That's the end game. The end game is to make sugar. If you're making a lot of sugar, the plants are healthy. If they are not making a lot of sugar, they are unhealthy. We are indirectly measuring then photosynthesis by measuring what? Sugar. We measure sugar. And when we do that, we can do so rather accurately and confidently, much better than some of the other tests that are out there. And the quickest way to do it is to test it with a refractometer. The Brix refractometer is the fastest way to go. How fast? About a minute. Take you about a minute to do the test. If you're a little slower, 2. And if you're really slow, it might take you 3 minutes or longer, but it's fast. And it's dirt cheap, too. You can buy one on Amazon for 20 bucks. It's not exactly going to break the bank. But we do have 2 types of refractometers that are out there. The first one off to the left, that's the $20 model. Take a look through the eyepiece here. Point it towards some light close to the sun, if not a fluorescent light indoors. Pop up the lid, squeeze, oftentimes with a garlic press, 2 or 3 drops out, and then look through the viewfinder, in order to determine the Brix level. There's going to be a line, and it'll be relatively easy to discern. If you don't like to use this, and you are technologically savvy means you know how to use batteries. When you put in batteries, you don't put them in upside down. You know the difference between a positive and a negative end. For those technologically savvy people, the digital refractometer is the way to go. That's the one that I have. Part of the reason I like that, not only because I understand the difference between positive and negative, but because I get point values. So I can determine whether the Brix level is 12.3 or 12.2. For your purposes, totally irrelevant. Really for mine as well. But I like knowing that it's either 12.2 or 12.3 because I have issues. I'm a scientist. This is the way we think. We like data, we like exact data. You don't need the 12.3, but the thing I like about the digital refractometer is that it's fast. And because it's fast, I can quickly get through a lot of readings and turn around and move through a farmer's field in order to determine where the Brix levels are. So let's talk a little bit about the insects right now. Are insects all the same? No. They better not be. We have over 1 million species of insect. They're all going after different things, every single one of them. Each one has their own story to tell. Therefore, grasshoppers and aphids are not the same. And pretty much everything in between. What exactly is the difference? Well, they have multiple differences, not just as far as appearance and size, but they also have a difference as far as digestive systems. The digestive system on a grasshopper is essentially, it's a tube within a tube because the grasshopper has an exoskeleton, which is a tube. The digestive system is a tube within that tube, and when it takes in food through the mouth, it goes in a unidirectional manner towards the anus, and then it is expelled. It's exactly what humans do. You get it, I get it. But things are different for the aphid. You can see that it's got a digestive system that folds back upon itself. Sure, food can still pass through in a unidirectional manner, but because the aphid system folds back upon itself, it has this weird structure that does some odd things, as indicated by the blue arrows. This actually pulls out that which it is eating, the food, and sends it directly to the hindgut and is expelled. What is it pulling out and expelling very rapidly? Predominantly sugar and water. because it's feeding on phloem tissue. It's getting too much water, it's getting too much sugar, and it must expel them. So if you go in for a dentist appointment, and you park your car or truck underneath a tree, and then you come out after another hour or two, however long you're in there, and your truck is sticky. That's because it was underneath a tree with Homopterous insects that are drinking the phloem tissue of the tree and pooping out the back end a very sugary water we call honeydew. Very attractive to ants. They like it. We obviously don't want it on our trucks, but this is the effect of these Homopterous insects. They have a way of filtering things out because if they allow water or too much sugar to get into this midgut, it will be absorbed. And the aphid cannot absorb that much water, and it cannot absorb that much sugar. So if this bypass mechanism is not there, the aphid dies. Nobody's going to shed any tears over that. I get it. They're just aphids. But they will die within seconds. They'll be dead within 1 minute. Because of this, that's why they have the bypass mechanism. And that makes a huge difference when it comes to understanding what Brix levels these insects can handle, the sugar levels. This is known as the Homopteran filter chamber. It's named after the original order, Homoptera. It includes aphids, it also includes leafhoppers and a number of other sucking insects, and that's what they do. Now, what are insects eating? Insects are eating food, and sometimes that takes the place of the course of proteins. Now, proteins are composed of a bunch of amino acids. These amino acids are all connected in a row, much like a train. And so in this particular case, I've just drawn randomly 33 amino acids up on the screen. And see, they're all connected as if they were by a train. If I were to break it apart using an enzyme, this enzyme, which doesn't work very well right here and is a bit amorphous, then combines with a cofactor. So my hypothetical enzyme hypothetically combines with a cofactor that is hypothetically manganese. It now forms a well-formed enzyme versus the bad form that we had before, and it's able to do its job. What is its job? Its job, in this hypothetical scene, is to break apart the protein at that point. The blue amino acids from the yellow amino acids. That is called digestion. We break apart food all of the time. First using our teeth, and then we have salivary amylases that break it down further, and then we break it down here. We can only eat or digest that which we can use as a food source. Anything we can't use as a food source, like a 2x4, we don't eat. Enzymes also do other things. They also form disulfide bridges. So these proteins will actually twist, turn, and actually connect in different spots. This allows a protein to form in these odd shapes. These odd shapes make the protein complete. A complete protein is made and then bends, forming disulfide bonds, and the protein is now considered to be complete. This is also accomplished by enzymes. So here we have an amorphous enzyme, and this hypothetical enzyme hypothetically needs zinc in order to do its job. In this particular case, it's to make disulfide bonds, which means they need to twist, turn, and make a complete protein. This is a picture, an actual picture of hemoglobin. Hemoglobin is composed of 4 proteins, which twist, turn, and have lots of disulfide bonds, which allow the red blood cell in order to do what it's supposed to do, which is to carry oxygen throughout the body. If it is malformed, like sickle cell anemia, it doesn't do its job, and the oxygen is not transported efficiently. So in other words, if we have an incomplete protein, incomplete proteins mess up systems. They mess up physiological systems. They might mess up this red blood cell, as they do in sickle cell anemia, but these incomplete proteins are a problem in many physiological processes. Dissolved nutrients. If you happen to go to the hospital, God forbid, maybe you have to have surgery, maybe you aren't able to eat, they hook you up to an IV. The IV contains two major things in addition to water, and that is amino acids and sugars. And this goes directly into your bloodstream. You will notice there's no pizza in here. You'll also notice that there's no cheeseburger in here. The reason why is because we cannot accept pizza and cheeseburgers directly into our blood. We must take it into our mouth and digest it. Once we digest it, it will then be transported around our blood, and the hospitals simply bypass that. These dissolved nutrients are easier to eat, get into our body if they come into the blood system. But if we need to break something down, we have an alternative way to get that done. Here are sugars. Fructose, galactose, glucose, all 6-carbon sugars known as monosaccharides. These are the sugars that we use as an energy source. Sometimes we can combine them into what is known as a disaccharide. A disaccharide contains 2 monosaccharides that are connected by a bond, which you can see right here with that oxygen bond. A disaccharide is composed of 2 sugar moieties, and the most common one is sucrose. Sucrose is known as table sugar. So if you're trying to put table sugar into your coffee, or maybe onto something that you wish to have a little bit more of sweetness to, you are using sucrose in order to do so. It is a disaccharide. Can we go further than a disaccharide? Absolutely. We can go to a trisaccharide, that composed of 3 sugars. And raffinose is one of those sugars that will also be transported around the plant, but you get an idea. We could have monosaccharides, disaccharides, trisaccharides, and we can go even further, and we do, to cellulose. Cellulose is composed of repeating glucose units. Glucose is the major sugar that we use as an energy source to get everything done, from seeing to breathing to digesting. Everything is about glucose. Cellulose is composed of repeating glucose units. What does that mean? Well, we should be able to use it as a food source then, because there's a lot of glucose in it. Why aren't we using it as a food source? This is the reason why. This crazy bond, this beta-1,4 glycosidic linkage cannot be broken by humans. We cannot digest cellulose. If you understand at the most fundamental level why we cannot digest cellulose, you now understand why insects cannot eat everything on the planet. You now understand why insects are only going after certain broken down compounds. You are now starting to understand why insects are only eating incomplete proteins, partially digested proteins, because a fully formed molecule is indigestible to an insect. Even if they were to eat it, they wouldn't be able to digest it, which means they can't use it as a food source. I think everyone is now on the same page. So, all of this sugar action, where does it go? Well, the plant certainly needs it. I just told you it makes cellulose. So therefore, it's going to be making the leaves, the stem, the roots, all that stuff is going to be made by glucose repeating units, which is made by photosynthesis. But about 40% of it is sent down to the roots and exuded into the soil. What for? I mean, this is its main job, is to make sugar. And almost half of it is being thrown down into the soil, wasted, gone. There's got to be a good reason for that. And of course there is. It's to feed the microbes. Why is it important to feed the microbes? Because the microbes are feeding the plant. Specifically, they're feeding the plant micronutrients, manganese, copper, iron, all of those micronutrients that form cofactors with the enzymes that I just got finished telling you about need to be moved into the plant using microbes. That's why it's important. The plant feeds the microbes by taking the excess, hopefully it has excess sugar, and throwing it down into the roots so that it can get those micronutrients, that it can do the job that it's supposed to do. That's why it does it. The amount varies a little bit. It's going to be anywhere between about 20 to 70%. If you have a higher Brix plant, they're going to be able to afford to put more sugar into the soil. A lower Brix plant will not be. If you do the math right now, if I'm dealing with a 4 Brix plant, it's only going to be able to send about 2 Brix of sugar down into the soil. Not enough to feed the soil microbes. If I have a 14 Brix plant, that's 7 Brix going down in there. That's enough to feed the microbes. That's the reason why this whole process exists. Now it's time to talk numbers. This is the chart that I made. It is a leaf Brix chart. I want to make sure that we see this up here, because in the third presentation, I'm going to start talking about different parts of the plant. But now, it's all about leaf Brix. This is a leaf Brix chart. You will see that the numbers run between 1 Brix up to about 20 Brix, and I stop. I do have 20 plus, but I stop. The reason why? I almost never get Brix readings above 20 when I'm testing a leaf. Therefore, I stop at that point. If there's any extra sugar, they don't fill out the leaves. They simply throw it into the soil. So you're usually maxing out at about 20 Brix. If I'm dealing with a plant and I measure its leaves and it's coming in at 1 to 2 Brix, force feeding is necessary. These plants are in trouble. They will not survive on their own. They need to be force fed. And so because of that, we force feed them. What am I talking about? I'm talking about golf courses, the greens. There's almost no photosynthesizing going on at the greens. They have to be fed daily. There is no day off on Sunday for them. They have to be fed every single day. If you don't, the greens will turn brown. And many people are no longer interested in playing on a golf course that has brown greens. So they have to be force-fed. Many house plants, usually outside, not exposed to the sun, are also going to be very low Brix, 1 to 2 Brix. These are the type of things they need to be coddled, they need to be taken care of, because as soon as you take that house plant and you move it outside, it can be dead in 24 hours or less in some circumstances. This gives you an idea of how weak some of these plants actually are. These are the lowest level plants that we have out there. In the next range, from about 3 to 7 Brix, these plants have a fighting chance. They're doing okay, not bad. Not great, but not bad. And they have a fighting chance at surviving. They have just enough sugar being produced in order to get basic things done, making a basic leaf, a basic stem, a basic root system. They can kind of do that, and that's about it. They're not able to do some of the higher functions that we often associate with plants. An interesting thing happens in this region, and that is at 6 Brix. Plant secondary metabolites increase. What are they? The plant secondary metabolites, they offer color, taste, smell to a plant. Things that maybe make it taste good. So what are you saying, Tom? You're saying that a plant below 6 Brix tastes like cardboard? Is that what you're trying to tell us? Yes. That's exactly what I'm telling you. If you've been around on this earth long enough, you have tasted stuff that tastes like cardboard. Either a fruit that tastes like cardboard or a vegetable that tastes like cardboard. And so yes, that's exactly what I'm saying. Things only start to pick up at 6 Brix. In the next region, between about 8 to 12, we've got a sword and a shield. The plant is able to defend itself. and it does a pretty good job of defending itself. It's not there yet, but it's close. These plants look much better than the plants between 3 to 7. They have some interesting characteristics, incredible water retention abilities. Why? I thought water retention had to do with the soil. No. Water retention has to deal with the microbes, because the microbes need water. Every single one of them has to take a sip of water, much less than a drop of water, but they need to take a sip of water. And so when you have 20,000 microbes in a spoonful of soil, you can kind of get an idea of how big this can get. If you have 200 million microbes in a spoonful of soil, that is some serious water retention there. And so when you have a higher Brix and more sugar is going down into the roots, we now have water retention. You can reduce your water 10%, 20%, 30%, 50% as you're going from 8 to 9 to 10 to 12 Brix. This is extremely valuable for Southern California, Arizona, New Mexico, parts of Colorado, wherever things are very, very dry. This is a very important characteristic because they're usually limited on how much water they have, and that's why when you get microbes in the soil, you're going to have a plant that survives the drought better than your neighbor's plants do. Insect resistance begins in earnest. Why? Because the secondary plant metabolites confer resistance. A lot of them are bitter. They've got some flavors that insects don't particularly like to eat. And so therefore, a lot of these flavonoids, terpenes, glucosinolates, whatever secondary plant metabolites you can think of, and there are tens of thousands of them, these are the type of things that are conferring a certain amount of resistance from the insects. The insects will not want to eat it when it gets at that point. And that's why insect resistance begins in this region. The plants between 12 to 20 are objectively healthy. You'll notice I did not put up the word subjectively healthy. This is not my opinion or your opinion. They are objectively healthy. You can use any type of test you want, and you will find that they are healthy on every single test that you can think of. They're objectively healthy. And they will look fantastic. These plants will look different, certainly between 3 to 7, and even better than the 8 to 12. Food is now produced. It's now fit for human consumption. What do I mean by that? Well, we want healthy food. If we want to live into our 70s, 80s, 90s, and beyond, we need to eat healthy food. We cannot be eating snack food and cupcakes all the time and expect to live a long life. We must have healthy food, and that's going to be about 12 Brix and above. So that's good for us. What's also good for us is that between 12 to 20 Brix, you have no more insects and no disease attacking your plants. So these are some of the shocking things that I've come here in order to tell you about. The details will come if you are interested in knowing why. But no insect will attack a plant between 12 to 20. No disease will take hold of a plant between 12 to 20. The higher the better. I prefer 14 Brix because there's usually going to be about a 2 Brix variability throughout the day, and sometimes it can go from week to week. 14 is safer because if it falls down to 12, it's still protected. So I'm always looking to get a 14 Brix if we can get it. So, I saw some of you taking pictures right now. This concludes this picture. If you're going to take a picture real quick, I'll get out of the way and I'm going to move on to the next slide. But this is the leaf Brix chart. It is available. It's been seen on the internet many times. I'm now explaining it in enough detail in order for it to be understood because we need to have this foundation. What do plants need in order to be high Brix? Well, this is the no-duh slide. But is it really no-duh? Do you really know that sunshine, water, air, and nutrients are required for a high Brix plant? And I would contend that most of you do not know this. Because if you are planting corn at 32 to 36,000 per acre, you don't know about sunshine. Because the corn isn't getting enough. And that's why the insects are attacking it. And that's why fungus infection moves in. because it is not healthy in order to raise that. Low Brix farming is expensive. In order to take care of your plants, you have to put down inputs. If they are high Brix, you don't need to put the inputs down, and it becomes less expensive. High Brix farming is not expensive, low Brix farming is expensive. So when you have sunshine, we need to make sure that we have adequate levels, because if they're too close to one another, they're not getting enough sun. And the Brix will reflect that. I can go out into a field and see that the Brix levels are too low. Water. We need to have enough water. Why? For the microbes, mostly. Most people think we just need to feed the plants. No. You need to make sure that the microbes have enough water. If they have enough to swim in, they're going to be in good shape. If they don't have enough, they dry out. Sometimes they die, other times they go into a dormant state. And if we get too much, the aerobic ones will die. We get this a lot in Florida. When we get a hurricane, we'll get flooding, and then they have to repopulate again once the waters recede. So too much aerobic microbes drown. We need to have enough air. If we do not have enough, the anaerobic microbes will proliferate. Did you know that you need air? Did you know that about 80% of the microbes in your soil should be aerobic, which means they need oxygen? Did you know that? Because if you don't have air in your soil, then you are going to have an anaerobic population, which is now going to increase. Aerobics, especially the Ascomycetes, are going to be releasing a chemical called geosmin. Geosmin is that odor which, when you smell healthy soil, it smells good. Sometimes you smell it after a rain, that good soil smell, that's geosmin. And that's caused by aerobic bacteria. If you have anaerobic bacteria taken over, what do you have? You have stinky, smelly soil. That's what you have. And that's when you know that there's a problem. Nutrients. What nutrients do you need? Well, shoot, you need all of them. Even the insignificant ones, like cobalt, which people don't usually think about. These are the type of things that are necessary if you need to keep a plant going. And it's not just about NPK. So, what do insects do? Are insects just going after unhealthy plants and they're not going to hit anything next door? Is that what you're saying? Because I don't think that's the way it works. And I would say, well, you're wrong, because that's exactly the way it works. You can have a sunflower that is absolutely ravaged and attacked by grasshoppers, as this one is. The surrounding ones have a few bites, a few nibbles coming out of them, relatively untouched. So it is very possible for you to have unhealthy plants in a batch of healthy ones. And you can see that in this picture, and if you take a closer look, you're not going to be able to see it here. The grasshoppers are attacking this in earnest. Same thing over here, we got a sago palm. You can see the scale insect, which is infecting this particular sago palm. Those are the small white dots. There is a break here. The plant is broken. Because it is broken, it is unhealthy from here until the tip. It is the unhealthy part that is being more seriously attacked by the scale insect. Exactly what you would expect. Exactly as you would predict. Because they're going after the unhealthiest portions of the plant, and that's where they concentrate. Same thing here. Here I've got a tree. Looks like a rather nondescript tree. Not too much to see here. But let me zoom in. If we zoom in on this tree, you can see that the tree bifurcates, which separates into two. There's one side, the right side, which is healthy, has good bark on it. The left side is dead. Because the left side is dead, that's where the Buprestid beetles and the Cerambycid beetles are laying their eggs. And those beetles are eating the dead wood. And then a woodpecker comes in and wants to eat them, because these beetles get to be between 1 to 2 inches long. It is a juicy, delectable morsel that they love, and that's why they beat their heads on the tree in order to get to it, and that's why they're leaving these holes in the dead part of the tree. These holes are not found on the live part of the tree because there are no beetles in that one. They're only on the dead side. So you can have a plant that is healthy, a plant that is unhealthy, and you can also have unhealthy parts on a relatively healthy plant too. So I'm teaching you as much as possible to make sure, again, feeding into you is the word that I will use to make sure that we understand this concept in totality. Here we got the same thing again. This is the Bupresti beetle right here, like the emerald ash borer. We have a Serendipity beetle right here, a longhorn beetle, beautiful beetle, prized in collections. Same thing is going on here. We have a tree. This is the healthy part of the tree. This is the dead part of the tree, which has been taken down by a chainsaw, and it is now riddled with woodpeckers. Why? The woodpeckers are only going after the beetles. That's all they're interested in. And that's why it's being ravaged right now. All right. Fall webworm. Fall webworm attacking pecans. Here we've got, give or take, there's about 50 fall webworm colonies on this particular pecan tree. It has dominated the tree, and this is obviously a sign that the tree is unhealthy. That's the one thing that you learn from this. On the other hand, we also have pecan trees that are not considered to be as unhealthy. There are exactly 3 fall webworm colonies on the tree to the right. Does this mean you can grade how healthy a tree is by how heavily infested it is? Yes. Yes, you can. This is going to be a higher Brix pecan tree. This will be a lower Brix pecan tree. And I didn't even need to use a refractometer in order to make that determination. And now you can make that determination as well. So this is the last slide. This is the beginning of the second talk that I will be doing. I've now superimposed insect groups, particular feeding guilds, onto the Brix chart that I just showed you, the leaf Brix chart. And you will see, I'm going to conclude with this slide, and this will obviously be the introduction to the second part. We'll take a quick few-minute break in just a second. But I need to tell you what's going on with this slide. Aphids, I call the aphid group, are going after the lowest level plants that are out there. They would prefer to go after 3, 4, 5 Brix. Once the Brix levels get up to about 6 or 7 in some cases, and by the time you get to 8 Brix, all the aphids are gone. Totally gone from the plants. Sucking insects, the other sucking insects, not just the aphids. These include the leafhoppers, froghoppers, plant hoppers, stink bugs, lantern flies. These are all the insects that are sucking on the plant, but they're not in the same category as the aphid. They will leave a plant once the Brix gets to 7 or 8, and by the time you get to 9 Brix, there are no more sucking insects on your plants. Next category, chewing insects. Chewing insects include the Lepidoptera, the butterflies and the moths. Those are the caterpillars, such as we saw with the fall webworm that are chewing upon the leaves. Beetles, chewing insects. They may chew on leaves, they may chew on the roots. These chewing insects will leave a plant or not touch it. Once it gets to 9 Brix, 10 Brix, or 11 Brix, depending upon the species. And the last group has impressed me about what they can eat. And those are the grasshopper groups. The grasshopper group include the grasshoppers, shorthorn grasshoppers, longhorn grasshoppers, the Teddigoneids. It also includes katydids, crickets. Those type of insects are in the grasshopper group, and they will not leave a plant until it hits 10 Brix. Sometimes 11 Brix, and sometimes 12. I have seen them taking nibbles out of a 12 Brix plant. They won't stay, they won't eat a lot, but they'll eat a little bit. And so because of that, the grasshopper group gets a little bit more distinction than the others. This is how I'll begin the second presentation, but this is how I conclude the first presentation.